In this lesson with triangles, we're going to look at isosceles and equilateral triangles specifically. Now, isosceles triangles, like the one shown here, have the following characteristics. The two sides of the triangle that have the same measurement are called the legs. Next, the two angles that are opposite the legs are called the base angles. Doesn't matter if they're on the bottom or on the side, because the triangle can be reoriented any direction that you need. It's their location relative to those congruent parts. So the two congruent angles are base angles. Next up, the one side that is a different length from the others is called the base. And our last piece is the one angle that is not the same as the others, and that is called the vertex angle. So we have legs, base angles, base, and vertex angles that make up the parts of an isosceles triangle. With this, and with the parts that are shown, we get a couple of theorems. First is Theorem 4.3, the isosceles triangle theorem. It states, if two sides of a triangle are congruent, then the angles opposite those sides are congruent as well. So here, our legs are congruent, and you notice that the base angles are congruent as well. Theorem 4.4 is simply the converse of Theorem 4.3. So it will read, simply if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Just like a converse, we switched our if and then statements. But this means that if I'm given two sides, I know information about the angles. If I know two angles, I know information about the sides if we're dealing with an isosceles triangle. So as we move on from this, we can use the idea of these congruent parts in order to find congruence in the triangles as a whole. So let's take a look at that. Using these theorems that were just given, and knowing that AC, line segment AC, is congruent to line segment CD, and the other information shown here in the diagram, we need to prove that angle A is congruent to angle BEA. So let's begin by marking up our triangle. So we know that AC, this side over here, is congruent to CD, this side here. And what we're looking for is to prove that angle A is congruent to angle BEA. Well, what do we know from here? We know that the large triangle, triangle ACD, is an isosceles triangle because we have a set of congruent line segments, and those base angles prove that to be true. Moving on, we know that in triangle BAE, we have a pair of congruent side lengths. So BA is congruent to BE. And according to the Theorem 4.3, if the line segments are congruent, then the angles opposite them would be congruent as well. So we can simply state that angle A is congruent to angle BEA by Theorem 4.3. And if we hadn't been given the fact about AC and CD, we would have been able to use angles A and D in Theorem 4.4 to prove their congruence as well. So with these theorems, we can move on and develop another idea. And that idea continues to develop off of isosceles triangles and is going to be Theorem 4-5. This one doesn't necessarily have a name to it, but Theorem 4.5 reads as follows. That if a line bisects the vertex angle of an isosceles triangle, then the line is also a perpendicular bisector of the base. So what this means is that if I have a triangle that I know to be an isosceles, meaning that we have congruent angles at the bases and congruent sides, and we were to drop a bisector of that vertex angle, that it's also a perpendicular bisector of the base. So it cuts our base into two parts. We have two right triangles that are going to be congruent by side, 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 and side angle side, and that when it hits that base, it does form a right angle. So we're going to use this fact and others that we've developed in order to prove a couple of other items that can come along with it. And we're going to extend this out in the process to include items regarding equilateral triangles. But first we need to talk about a type of item. We've had postulates and theorems so far in our study of geometry. We're going to be talking about what's called a corollary real quick. And a corollary is simply a name given to a theorem that can be proved easily using another theorem. And because corollaries are theorems of a sort, we can use them to help prove as justifications as we're proving items and relationships amongst our geometric figures. So let's take a look at a couple of corollaries and how they relate to all of our work. Corollary to Theorem 4.3 states as follows. Simply that if a triangle is equilateral, then it is also equiangular. And the way we can justify this is that if we have a triangle where all sides are congruent, and we were to use Theorem 4.3 that says that if you have two congruent side lengths, then the angles opposite them would be congruent. Well, what happens if I were to change the orientation and say that these are my side lengths that make it isosceles, and this is the base here, then the angles opposite would be congruent as well. And now we have all three angles being the same, which is the definition of equiangular. The corollary to Theorem 4.4 follows similarly. It states that if a triangle is equiangular, then the triangle is equilateral. So again, I come up with a triangle, and this time I know that my angles are all congruent. Well, if these two angles are congruent, then Theorem 4.4 tells me that the sides opposite are congruent. But if I were to change my orientation again and say that this angle and this angle are my base angles, then the sides opposite them would be congruent, and now I've established that all three sides are. So being able to use these ideas of congruence in a single shape, let alone as we project it out to congruence between shapes, is going to be very important as we develop these ideas and start getting to more complicated structures, because most structures and shapes can actually be broken down into series of triangles. So make sure you have these theorems and now corollaries down so that we can use them in our proofs and justifications.